Hey, this is Mr. Ariel. I'm here today with a lesson about a concept called VSEPR, and we'll also get some information about molecule shapes. We've learned a lot about atomic bonding, and it's time to see what this stuff kind of looks like in real life. Let's go ahead and get started. So first up, VSEPR is an acronym. It stands for Valence Shell Electron Pair Repulsion. Get that name into your notes, along with this explanation that electron pairs in a molecule will repel each other. Another word for that is repulsion. Now, the repulsion between pairs causes the molecule shape to adjust, and last, the electron pairs will always end up as far apart as they possibly can. Now pause the video, get that into your notes, but I want to show you a quick example of what this all means, and we'll get into some more specific details after that. Let me take you over to an online simulation, and here I have two atoms bonded together. This is the single bond that's between them. Now this VSEPR concept comes into play if I add more atoms. Let me add one more atom to the picture. There it is. Notice that new atom is 180 degrees away from the first atom over here, and that's because those electron pairs that are part of these two bonds, they're as far apart as possible. If I add another atom, notice they all settle in at 120 degree angles. Each one of these lines is a covalent bond, and inside each bond is a pair of electrons. So VSEPR is about how these valence electrons involved in bonds will repel each other, and that determines the overall shape of the molecule. Now let's get back to the notes. We have a lot more to do there today. Now I want you to set up a table in your notes. You can see the headings for each column. Now be sure to leave a chunk of blank space. Probably 7 to 8 lines will do the trick. Leave that blank space up above the table. We'll add some details there line by line as we go through the table. So pause the video and set up your table, and then come back and we'll learn some concepts about VSEPR. Now the first molecule we're going to look at today is CO2, that's carbon dioxide. Now don't write anything in this box just yet. I want to show you the method that I showed you in a previous video, and I was just trying to teach you about covalent bonds. We would have said that carbon has 4 valence electrons, and then oxygen has 6, and if we wanted a covalent bond, we'd have these 6 electrons from oxygen, and then we'd reach out and grab those 2 from carbon. And we could do the same thing for the other, oxygen over here. And that gives each oxygen 8 valence electrons. And then for carbon, it can find 8 valence electrons by borrowing 2 from each of the oxygens. And so everybody has a stable octet. And remembering that we draw those in, those shared pairs, we draw them in as lines, like this. The final answer on this would look like this. Now, I know I showed you this method in a previous lesson, but it was just to make a point about how electrons are shared in a covalent bond. But all these circles, they get kind of messy and they're confusing to deal with, especially when you get to bigger molecules. So now that you understand how a covalent bond works, it's time to learn the faster and frankly more efficient method for drawing Lewis structures. I'll show you each step up in the area up here. So be sure to go ahead and write this first step down in the space that I told you to leave blank above the table. So the first step is to count up the total number of valence electrons. Well, I'm going to do that inside the box for the formula. Carbon is in group 14, so it's got 4 valence electrons. And then oxygen is in group 16, but there's 2 of them. And so we're going to multiply 2 by the 6 valence electrons that each one has. And so if we add that up, that works out to be 16 valence electrons that we have to deal with. Now the next step is to determine the central atom, and there are some guidelines for that. First up, it's usually the atom with the lowest electronegativity. After that, the rules say that it will never be hydrogen, but it will often be carbon. Now I'm only going to show the periodic table part once. I'll skip it for all the other examples. But here we can see that oxygen's electronegativity, well, that's 3.5. I'm going to write it below the element. And then carbon's electronegativity is 2.5. So if we want the lowest electronegativity to be the central atom, well, that's going to be carbon. And so I'll put my oxygen and the other oxygen over here. Now the next step is to draw single bonds to connect everything together and subtract the valence electrons that we've used. So I'm going to say that I have 16 electrons up here, but I need to draw single bonds. And if you remember, each bond is 2 electrons. And so I'm going to multiply 2 by the 2 electrons that are inside those 2 bonds. And if we work out that math, 16 minus 4, that works out to be 12 electrons that we have left over. So the next step is to place the remaining valence electrons around the atoms. So with 12 electrons and 2 oxygens, I'm just going to put 6 of them around each oxygen. And I'm choosing to do that because oxygen has the lower electronegativity. I don't think it really matters, but I just choose it that way as a pattern, because you could put some on carbon. And if you did, you'd still end up getting to the same answer on this next step. Step 5 says we need to add double or triple bonds until all atoms have a complete octet, or a full outer shell. And if you look right here, oxygen has 2 electrons, 2 more, it's got 2 more, and then these right here count as 2. So that oxygen has 8 valence electrons. And the same would be true over here. But this carbon right here, well, it's only got these 2 electrons and those 2. So carbon right now only has 4 valence electrons. So I'm going to try making a double bond here, but that would require 2 electrons. So I'm actually going to erase these 2 electrons from oxygen. And now I'm putting those 2 electrons back, but they're in a bond between carbon and oxygen. So this is a double bond now. And so if you think about it, now we've got 3 bonds around carbon, so that's not 4 electrons, now we've got 6. And so if I do the same trick and take those 2 electrons off the right-hand side, well, I can put them back here, and so now it's not 6 electrons, I've got 4 bonds, and that's going to be 8 valence electrons. Now for this shape, let me take you back over to the simulation, and if I build this molecule, here's carbon that's in the middle, and then I'm going to add on 2 double-bonded oxygens, just like this. And so you can see here that that bond angle is 180 degrees between the 2 oxygens. Remember that part of the VSEPR model is that the electron pairs, the ones that are part of these bonds, they arrange themselves to be as far apart as possible. And that makes the molecule look like a straight line. So I'm going to click on Molecule Geometry, and the simulation is telling me that the name of this shape is linear. So thankfully it kind of makes sense. Now going back to my notes, I've added the shape name to the box. And the next thing we need to do is make a 2D drawing of a 3-dimensional shape. Now it ends up looking the exact same as what we drew for the Lewis structure over here, but that's not going to be the case for many of the other molecules we do today. Now last up, we're going to look at whether the overall molecule is polar or not. We already learned about how to tell whether bonds are polar covalent or non-polar covalent. It's about that difference in electronegativity. If the difference is between 0.3 and 1.7, we've got a polar covalent bond. Well, for oxygen and carbon, that was 3.5 and 2.5, so if I subtract those, I get 1.0, and that's solidly in the middle of polar covalent bonds. Now, oxygen is more electronegative, and that means it pulls the electrons. Remember last time we were drawing them with an arrow like this to show that those electrons spend more time around oxygen? I'm not going to draw that arrow much today. I'm going to focus on this other method of showing it, that we have that partial negative charge because those electrons spend more time around oxygen, and then there's the partial positive charge that's on carbon. Now you might be thinking that makes the molecule polar, but it doesn't. It's nonpolar because it only has partially negative ends. To be polar, you'd have to have a positive at one end and a negative at the other end. It's kind of like the poles of the Earth. The Earth doesn't just have a North Pole or just a South Pole, it's got to have one of both. If that's confusing right now, hang on, it'll probably make a little more sense when we get some more practice. So let's move on to water. We're going to try that. The formula is H2O. And this will be a little faster because we already have all the rules. So counting up the total valence electrons, well, each hydrogen that has 1, and so I'm multiplying by 2, and then we're going to add on the 6 valence electrons that oxygen has. So that's 8 electrons. Next, we're going to determine the central atom, but the rules say that can never be hydrogen, and so it's got to be oxygen. So I'll put oxygen right here in the middle. I'll put hydrogen on each side because we have 2 of them. Then we'll draw single bonds to connect everything together. And now I've got to remember to keep track of those electrons. We had 8 electrons, and now we used up 2 in one bond and 2 in the other. So that's 2 times 2. And so 8 minus 4 works out to be 4 electrons. So now we're going to place those remaining valence electrons around the atoms, but hydrogen can't hold any more valence electrons. It's already got its 2 electrons that it can possibly hold as part of that bond. So I'm going to put those remaining electrons on oxygen. Step 5 is add double and triple bonds until all atoms have a complete octet or a full outer shell. Well, hydrogens, they both have a full outer shell with 2 electrons. And if we count up around oxygen, it's got 1, 2, 3, 4 down here, and then 5, 6, and 7, 8 with that other bond, so we don't need any double or triple bonds. Now for the shape, we need to go build this molecule over in the simulation. So I've got that central oxygen, and now I'm going to add on 2 hydrogens, And it kind of looks like it's a linear molecule, kind of like I drew into the notes. But let's not forget that we have two pairs of electrons that belong to that central oxygen. So let me add those in. Notice that just shifted the shape a little bit, and I've got to add in one more pair of electrons, just like this. If you notice the molecule is now kind of bent, that's the actual name of the molecular shape. So let me go back to the notes. And so I've got that name of the shape recorded, and now we're going to try to do a 2D drawing of a 3D shape. And it's going to be this Lewis structure again, but this time we're going to try to draw it so it reflects a little bit of that actual shape. So I'm going to draw it like this. And then those are the unshared pairs of electrons. Now for the last thing, whether this molecule is polar or not, oxygen's electronegativity is 3.5. I'm putting it back under the formula. And hydrogen's electronegativity is 2.1. So if we subtract those, 3.5 minus 2.1, that works out to be 1.4, which is definitely still between the ranges we need for polar covalent. And with oxygen being more electronegative, that means this end of the water molecule is partially negative, and then each of the hydrogens is actually partially positive. Now on the previous example with carbon dioxide, that partially positive carbon was surrounded by negative oxygens, and so that made it non-polar. But this water molecule is actually polar, and that's because it has both partially positive and partially negative ends. Like this negative sticks out from the edge of the molecule, and the positives also stick out from the edge. Now make sure you've got all this into your notes, and when you do that, also draw one more row into your table, because I'm going to add one more example, but I want to clear off most of this from my screen. All right, if you've drawn that new row, let's fill it in with a new formula. That's going to be CH2 with an oxygen. Let's do the total number of valence electrons. Carbon has 4. There are 2 hydrogens that have 1 each, and then oxygen, that one has 6 valence electrons. So if I add that up, 4 plus 2 plus 6, that makes 12 electrons. And then we need the central atom, and that's going to be the one with the lowest electronegativity. And hydrogen, that's 2.1, oxygen is 3.5, and carbon is 2.5. So hydrogen is the lowest electronegativity, but the rules say it can never be hydrogen. And so that means we're going to go with carbon. So I'll put carbon right in the middle. I'm going to put an oxygen over here. I'll put a hydrogen, and I'll put the other one right here. Next up, we need to draw single bonds and subtract the valence electrons. So that's going to take 3 single bonds. And I'll take my 12 electrons, and I'm going to subtract off 2, 4, and 6, because there are 2 electrons in every bond. That's 3 times 2. So 12 minus 6 works out to be 6 electrons left over, and we're going to place those remaining valence electrons around the atoms. I'm just going to choose to put them on oxygen, because it's more electronegative, but it really wouldn't matter if you put 4 on oxygen and put 2 on carbon. You'd still get to the same answer here in a second. Now the last step, we need to add double or triple bonds until all the atoms have a complete outer shell. And right now, hydrogen is good. They both have 2 valence electrons each, and that's all they can hold. And my oxygen over here has 2, 4, 6, plus 2 more. That makes 8 valence electrons. And so carbon over here is the only one that doesn't have a full outer shell. It's only got 6 valence electrons. And so we're going to take 2 off of oxygen and just use them to make a double bond. So there we go. Now everybody's got a full outer shell. Now for the shape, let's go back to the simulator. And here's my central carbon. I'm going to add on 2 hydrogens just like this. And now I'm going to add that double bonded oxygen back to the picture. All right, there we go. Notice that all of these bond angles are 120 degrees. This shape is called trigonal planar, and it's trigonal because it's like a triangle. And then it's planar because all of these atoms exist in the same plane as each other, like in geometry. So going back to the notes, I've got that shape recorded, and then we'll do a 2D drawing of that 3D shape, but I want this drawing to kind of reflect those 120 degree bond angles. So I'm going to put my hydrogens kind of like this, and then I'll put my double bonded oxygen right there. And then I need those unshared pairs. Now, if the molecule is polar, that's because it has positive and negative ends that kind of protrude from the edges of the molecule. So looking at the bond between carbon and hydrogen, that difference right here is 0.4. And so that's definitely still a polar covalent bond. And so that means this end of the molecule is positive, and so is this one. And then for the bond between carbon and oxygen, that's 2.1 and 3.5. So that works out to be a difference of 1.4, which is also polar covalent. And with oxygen having the biggest electronegativity, that means this end of the molecule is actually partially negative. And so there you go. You've got two positive ends and you've got a negative end, so this molecule is definitely polar. And that's because it has both partially positive and partially negative ends that all protrude off the edges of the molecule. If everything on the outside was positive or everything was negative, the molecule itself would be nonpolar. Again, you got to think about it like the poles of the Earth. The Earth doesn't just have a north pole or just a south. To have poles, you have to have one of each. Now there are several more molecule shapes to learn about, but this video has gone on long enough. We'll save those other shapes for another lesson. For now, if you've got all of these ideas into your notes, you're all done with this set. I hope the video has been helpful to you today, and as always, thanks for watching.